Day 68, page 272, rotational kinematics, problem number 29. So the first thing I have, I've converted from 1500 RPMs to radians per second. The simplified form is just to multiply by pi over 30, which is basically 2 pi r, or I'm sorry, 2 pi over 60 seconds. One full circle is 2 pi radians in 60 seconds. So that converts into radians per second. And then your 200 turns, convert that into radians. Each turn is 2 pi radians. So you have a total angular displacement of 400 pi radians. And then you just use your 5 quantities. Omega I, your initial starting angular velocity is 0. The final ending velocity, angular velocity, is 157 radians per second through an angle of 400 radians, 400 pi radians. So I'm using what we use as our second uniform acceleration equation, uniform angular acceleration equation. Theta equals 1/2 omega I plus omega f times t. Basically, this is the average velocity, average angular velocity times time, which is how we're supposed to do it in part B. So it's really the same problem in part B. So there's our theta, plug it all in, find t. Part B here, it's the same thing. Omega average, the definition of average angular velocity is your angle displacement over the time, total time. So delta t here just means t, because in our problems we're always going to pick t initial as 0. So that's why I usually don't put delta t in our problem, because we're going to take, like I say, t sub I as 0 every time. But there it is, basically, once again, your average angular velocity. So your total time, the time down here, will be, just switch them around, to be 400 pi divided by the 78.5, which is the same thing you're going to get in the portion here in part A, that I did in red.